Hello, everyone.
Good afternoon. Laviet.
Okay, today we have not sure four presenter, right?
Yes.
Okay, the first is Adamu. If you're ready, you can share your screen and let's start.
Okay, I'm ready.
Yeah, okay.
Okay. Good afternoon, all. My name is Adam Yusupinua, and I'm going to present my topic, my talk on one-step iterative method for bilevel equivalent problem in Hilbert space. Okay, this is the outline of my presentation. This is the overview. Okay. Yeah, me too. Okay, it's now on. Sorry for that. The first section of this, in the first section, will define equilibrium problems, example, and some as well as some of the application. Then we will go to some basic definition, and later on in the third section, we'll look at some relevant work that are related to our research, and then finally we will give our result in the last section. Okay, what is an equilibrium problem? Equilibrium problem is a problem of finding a point. If you have an empty set K and you have a bifunction F, which is dependent on K cross K into R, then the equilibrium problem is a problem of finding a point X tilde in K, such that F of X tilde comma Y is bigger than or equal to 0 for every point Y in K. And we denote this problem by E P of KF, and the solutions, it's a solution set by E of KF, and this term is coined by Utley in 1992 while he was. And then why do we study this problem? Because it is a very important class of function which generalize a lot of optimization problems such as fixed point problem, minimization problem, variation inequality, Pareto optimization, complementary problem, two-player zero-sum games, and many other problems. Then just my slide. And this equilibrium problem has many applications such as game theory. Specific example is the prisoner's dilemma, where it also has application in eco-industrial park mean variance, and also it has application in mean variance portfolio. Okay, now we go to the second part, which is the preliminaries. Okay, we start by a compact set. So a set is said to be compact if whenever you have an open covering of the set, it can be reduced to a finite subcovering. And then we say that a set is compact, is convex if and only if when you take any 2 points, you can just join the 2 points by a straight line which stay completely inside the set. We can see that, for example, if you look at this first set, this is convex, because if you take any 2 points, you can always join them. But the second set here is not convex. As you see, for example, if I take this point and this one, I cannot join them by a straight line without a straight line going out of the set. Then I have what is a convex function. A convex function is a real body function set to be convex if it satisfies relation 6. And for graphically, maybe a function which looks like a parabola, an upward-looking parabola. For example, this one is a convex function, because if you draw any, in fact, the function is set to be convex if whenever you draw a line connecting 2 points on the graph of the function, the graph of the functions lies below the line. This one is not a convex function, because if you look at these 2 points, when you join them, the graph stays above the straight line connecting the 2 points. And so now look at the geodesic spaces. So if you have a metric space, then a geodesic path connecting a 2 points U and W in the set is just a mapping from 0L into H, such that gamma of 0 is the first point and gamma of L is the second point W, and that it satisfies this relationship. If you take any 2 points, we have gamma, the distance between alpha of gamma of T, comma gamma of S is the same thing as T absolute value of T minus S for every T and S in 0L. And the image set of gamma is called the geodesic segment connecting U and W. And when it is unique, we denote it by U, comma W in this using this notation. So if it happens that if you take any 2 points in a space, then you can connect them by a geodesic segment, then we call that a geodesic space. And when those mappings are unique, then we call the space a unique geodesic space. Then we have geodesic triangle, comparison triangle. Then we also have a cut 0 space. Another important thing is the personalization map, which is defined by this relationship, which is defined on H cross H into H times H cross H. Actually, basically, this what does it kind of generalizes the inner product. It generalizes the inner product from the linear space into the Hadamard space into the cut 0 geodesic spaces. And now we go to look at bounded by functions. So you said that a function is pi uniformly bounded if you can always find a non-decreasing continuous function by phi from R plus into R plus, such that for some fixed point X naught in H, we have this relationship. And the function is said to be monotone if for every point U and B in K, we have this. And it's strongly monotone if we have this relationship. And what you can observe is that every strongly eta monotone function is basically a monotone function. And now we define another type of function. We say that F is set to satisfy a Lipschitz type condition with Lipschitz constant M, which is given by this, if this relationship, which is section 7, is satisfied for every point X, Y, Z in the set K. Where this function Bi satisfied this relationship is just some kind of generation of a Lipschitz continuous map. Here we have it's defined now on H cross H, and AI also satisfies this relationship. So this is actually a repetition of, I have already defined this one as a repetition. Now literature review. So, okay. The first method for solving equilibrium problem is the programmable point method, which was introduced early by Konob and Modafi in 1999 and 2003, respectively. They are the first people to use it on solving equilibrium problem. And this is how they use the method was, suppose we take a point X naught in K, then they use the programmable point method to generate the next iterate Xn by solving the following problem. So to get Xn plus 1, you solve this problem, where Rn is bigger than or equal to R, which is bigger than 0. And another method for solving this is the extra-gradient method also. One thing to note is that these two methods, the solution that you obtain is not the convergence you obtain is not strong. It's weak convergence, unless if you add some additional condition. That is if you are dealing with the problem is in a Hilbert space, the convergence you normally obtain is not strong convergence, but rather weak convergence, unless if you add some additional condition. So in order to obtain to get strong convergence, what is normally done is you sometimes combine this two methods by other method, such as the hybrid solution projection method, hyper iteration, and so on. And one added element of this by adding those, by combining this method, the solution we obtain also solves this problem, which we call the variable optimization problem, which whereby we minimize, you look for a point in the set of solution of the equilibrium problem, which is the closest to the point x bar in x. Maybe suppose you take a point x bar in h, then the variable optimization problem is the problem of finding a point in the solution set of the equilibrium problem, which is closest to the point x bar. So this problem is very important. It has many applications. And it's one of the generation is what the main problem we are concerned with, which is the variable equilibrium problem. This one is the generation of the variable optimization problem. So here the variable equilibrium problem is the problem is this problem of finding u tilde in the solution set of the equilibrium problem f such that f of u tilde comma u star is bigger than or equal to 0 for every point in the solution set of the equilibrium problem. We identify this problem by BEP. This in 2010, Modapi used the regularization program method in order to solve this variable equilibrium problem. And then recently, Shabani and Riahi, they introduced the proximal expansion and proximal splitting algorithm and use it to solve this variable equilibrium problem in Hilbert space. And they both analyze the weak and strong convergence of their algorithms. And then last year, How and Kwai proposed an iterative scheme where only one strongly convex program needs to be handled at each iteration in order to solve the equilibrium problem. Actually, most of the algorithm developed earlier, maybe the one by Modapi, Shabani, and Riahi, all of them, they use in the algorithm, you always have about 2 or 3 complex programming that need to be solved in order to find the solution. But in this work for this by PAM and what they produce is they produce an algorithm whereby you only need to solve one complex program and at each iteration in order to solve the problem. So our main work is what we did. These guys, they do their work in Hilbert space. What we do, we analyze their problem into KMUTT space. Okay, so now we define the regularized problem. So here we regularize the problem by alpha and the mapping cal f, which is a uniformly bounded function, and we define the regularized problem by this relationship. And also we assume that we make the following assumption on the function f. We assume that the function is monotone and that f of x comma x 0 for every point x in h. Also, we assume that it's eta strongly monotone, and we also assume that it is convex and lower semi-continuous in the second coordinate, and also it is upper semi-continuous in the first coordinate. And we also assume that the function f satisfies the Lipschitz type condition, and we also assume that the solution set of EKF is non-empty. So with this assumption, we have the following lemma 1, which defines a relationship between the, in terms of the proximal operator of the function, which is the operator is defined in this. Now we have another lemma which we have this lemma which talks about the sequence we obtain from the sequence x lambda and the next x lambda. And another lemma is lemma 3. We have this one also. Then now we define our algorithm by this. We just what you do, the first step, you take a point x naught in K, and we consider it takes two sequences of multivariate numbers alpha n and lambda n. Then we define the iterative space in terms of this proximal operator. Then we have lemma 4. also have this corollary which follows from lemma 4 by taking lambda in the first in one we take lemma 1 gamma 1 as equal to gamma 2. Here we take the lambdas at the same. We have this, and then we have, and then the next lemma, and with this we are able to, if the sequence lambda n and gamma n satisfy these conditions, these properties, then we are able to get our own strong convergence result. I think that's all. Thank you for listening.
Thank you for your nice presentation. Any question or suggestion to him?
Yes, thank you very much for
Okay.
the wonderful presentation. I would like to comment your presentation first, and then before then, my question is with regard to the Pareto optimization that you said you are going to present, but I didn't see it.
I didn't say I'm going to
anything.
present. I did not say I present. I said that one of the reason why we study equilibrium is that it generalizes many important class of problems. So one of the subclasses of problem of equilibrium problem is the Pareto optimization. It's in fact the Pareto optimization is a subclass of the equilibrium problem. That's what I said.
Hmm? No, I can meet him personally because actually, you see, as you said, the multi-objective optimization is a subclass of equilibrium problem. I can also say that vector optimization, multi-objective optimization, multi-criteria optimization are all subclass of vector optimization. So, in what sense can you relate equilibrium problem with vector optimization? They are all subclass, since multi-objectives is also a subclass of equilibrium problem. Maybe we can see to that. Maybe we can talk maybe personally on
Okay.
that.
Okay.
Yeah. Thank you very much.
Okay, no problem. Thank you also.
Any question? I see Adamu
Yes.
in this slide. In this slide, maybe in the first line, maybe you can delete is 38 is right. You
What?
can the reference. What? No. Come back. No. It's the slide. Same slide.
Good.
No, you come back to the slide when you show for Jamil.
Jamil.
Yeah, I think it's in the reference. You can delete the number of the reference in the slide. Right, you understand me? Yeah, and I see
this one, like this one.
Yeah, no. Yeah, you can use reference same this page, but last page you not use the same here. You have a reference this, you have a name,
Okay,
right?
okay.
And after that you have a number of the reference. Maybe you forgot delete maybe. And this I see some slide. I can go next. Yeah. Up. No, come back. Come back. Yeah, in here. in the first line in maybe 5 or 3, I'm not sure. Maybe you have the,
Yeah.
yeah, you have, no, first line. Okay, we discuss after, we tell you after that.
Okay, thank you.
Okay, thank you. Any question or suggestion? Yeah. If no any question, thank you, Adamu.
Okay, thank you all.
Okay.
Thank you all for your time. Thank you.
Second presenter is Mr.
Saan magkatambay, Abel?
Pavisha Phairat Chat Niyom. Pivi, are you ready?
Okay. Can you hear
If
me?
you're- Yeah, it's clear.
Okay.
If you're ready,
Can I
you
start?
can start. Yeah.
Okay. Okay. Let me share screen. Okay. Can you see my screen?
Yeah.
Okay. Thank you. So, I'm done now. Okay. Good afternoon, everyone. My name is Pravicha Bharataniam, and today I'm going to present my dissertation on the title Iterative Methods for Solving Inclusion Problem Involving Nonlinear Operators. So I have 3 sections with including with the introduction, main results, and numerical experiments. And let's move on to the first session. Okay. In this study, I have started an iterative method to approximate the solution of split relational equation problem and the fixed point problem. Okay, so let me recall the first problem, that is fixed point problem. The fixed point problem is the problem of finding the point star, let's say that star in the Hilbert space. Yes, in the Hilbert space, such that it's equal to its image under mapping T. Here T is a single value mapping, and we use fixed T to denote the set of the solution of the problem one by one. And fixed point problem is a powerful problem in the nonlinear analysis, provided the essential tools for solving nonlinear problems. Let's say that if you have a difficulty problem, sometimes you can write at the fixed point problem, which is make you solve the problem easier. Okay, then the next problem is a split relational equation problem. It is the problem of finding a star in the first Hilbert space, which is called 0 point, such that 0 belongs to the set of P1 over a star, and 0 belongs to the set of B2 of a star. Here B1 and B2 are maximum monotone mapping, which is a multi-value mapping, and A is a linear bounded operator from H1 to from Hilbert space H1 to H2. And we use omega SVIP to denote the set of the problem to number 1.2. And we also studied the split relational equation and fixed point problem, which is the problem of split relational equation problem together with the fixed point problem. here we consider the mapping T in the case of single value mapping, and we use this intersection with the omega SVIP to denote the set of the problem number 1.3. Okay, split relational equation problem is a uniform framework for many mathematical problems such as a split feasibility problem, piecewise problem, linear inverse problem, and rational equation problem. And it also applies to the river problem in the sensor networks in the computer science, tomography, and data compression. And this is let's say that if let's say that the split relational inclusion problem can be written at the fixed point problem like this, where J lambda B1 and J lambda B2 is called resolvent operator of B1 and B2, defined like this. Yes, gamma is a positive constant and is a step size, and I here is an identity operator on a Hilbert space S1, and S star is a joy of a bounded linear operator A. Okay, so what is the iterative method? The iterative method is a mathematical procedure that you start with the initial point. Here we use x0, and then the sequence the estimate to the next the next iterative. Let's say that x1. Okay, then the sequence generate like this, and then you will get a2, a3, a4 to xn until it's convert to the estimate solution x star. Okay, so in order to solve the split relational equation problem, Bernadette introduced the sequence defined by number 1.5, and here the condition of step size gamma n belong to this set, and this sequence provide the weakly convergent. Okay, in my research, actually, I'm studying many factors to improve the sequence. Let's say that I'm first start with the initial points. Sometimes you can use just one point, or you can use the initial method, which is you must to start with the two initial points, and also they have a and also they have another type of initial method, and maybe you can consider the step size of a parameter gamma n. You can use a positive constant or sometimes sequence like search or self-adaptive step size, and also the parameter lambda. Sometimes you can consider just positive constant or the sequence, or sometimes we combine this sequence together with another method like Cousin SHK iteration, minor iteration, Ishikawa iteration, because this is for example. Okay, this I provide you the sequence here to see the iterative methods. This is there are these are a famous method that if you study the iteration method, you mostly you mostly find the sequence. And also, this is the class of a non-implicit mapping. Let's say that when you store the nonlinear mapping, the famous one, it should be non-implicit mapping. And also another class of a non-implicit mapping, like firmly non-implicit mapping, or monotone, or alpha strongly monotone, or beta inverse strongly monotone, for example. Okay, in my work, I'm focused on the initial method for the starting point, and the next one is self-additive step size of a sequence gamma n. Okay, now I'm going to the main result section. This section is we study the iterative method for solving split relational regression problem and fixed point problem. And this is my my algorithm. Okay, and yes, and this is my algorithm. We start from the step 0 and then calculate sequence gamma n, and then we go to the step 1, step 2, if satisfy this condition, and then let's algorithm stop. Okay, and this is the strong convergence theorem. I just showed the convergence theorem only, and I omit the proof here because it's a long proof. So the main highlight, it should be the condition. So to get the strong convergence theorem, the necessary condition is here. So okay, I'm going to the last session, numerical experiment. I'm start with this example where mapping T, A, B1 and B2 defined like this on the real line. Yes, okay. For compare the algorithm, for test our algorithm, we compare our algorithm with the Krasniov-Sesky iteration and Burundi algorithm, and we should and we set the parameter like this, and we consider in two cases. The case one is we consider the variance value of initial point, and we fix parameter lambda, and otherwise we consider the variance value of lambda, and we fix initial point S0. Okay, this is the result of the case number 1. And okay, this is a Krasniov-Sesky iteration. This is a Burundi algorithm, and this is our algorithm. Okay, this is the graph, the graph of the first case. Yes, we see that the Krasniov-Sesky iteration and our algorithm converge faster than the Burundi algorithm. And this is case number 2. We consider the variant values of lambda, and this is Krasnodębski iteration, and this is Beringian algorithm, and the last one is our algorithm. And this is the case for and this is the graph of case number 2. We see that our algorithm is depend on the value of lambda, but it's not much if we compare with the Krasnodębski iteration and Beringian algorithm. Yes, and one more example where the mapping T A B1 and B2 defined like this. So and we fix the parameter of our algorithms, and one algorithm is algorithm of Chehu and ABC algorithms. And now we consider 2 cases as well. And this is the result of the first case. We can see that our algorithm converges faster and more accuracy than the Chehu and ABC algorithm. Sorry. Okay. Oh, yes, and this is case number 2. We can see from the graph that our algorithm converges faster than the Chehu and ABC algorithm. Okay, that's it. Thank you very much.น้องหมี
Any question or suggestion? No question?
Okay, good.
Really? Sunny, you don't have question? Okay, if no any question, thank you for nice presentation.
Okay, thank you very much.
Can you
Thank you
stop
all.
your screen?
Okay,
And the next presenter is Mr. Ahmed, right?
ไม่ใช่พี่เจียเหรอ เห็นชื่อแป๊บๆพี่เจีย
เงียบไว้
อ้าวอย่างนี้ได้โอเค โอเค โอเค โอเค
Okay, Ahmed, you
Yeah,
ready?
I'm trying to share my screen.
Okay, you can share your screen and let's start. I have questions, Solomon. Solomon, you want to present on Wednesday, right?
Yes.
Okay. Can you share your screen, Ahmed?
Yeah, that is what I'm battling with. Yeah, can you see it now?
Yeah,
Hello?
I see your screen. I see your
Yeah.
screen.
Okay.
I have to click on the You can
Open
only see
the
the
file.
items, not
Open your file.
Dr. Jamilu, where should I? Okay, is it okay now?
we can't see anything. We can only see the file Zoom, install, Abdulhab, inf, and what have you. Just click on it so that we can see the file. You are sharing the whole screen, not the work.
What happened?
If you can,
Okay, okay, good.
yeah, I see your screen, and please double click for open your file. Ahmed, you can send your slide in the chat. I can share slide for you.
Okay.
Okay, okay.
Okay, can I send it to the chat, or should I send it personally to you?
Yeah, you can. Yeah, you can share your screen. It's okay. It's okay.
Can you see it now?
Yeah, I see.
Dr. Jamilu, can you see my screen now?
Yeah, I think everyone can see.
Okay.
Okay.
Okay, so good afternoon, everyone. My name is Abdulhab Ahmad. The topic of my presentation is inertial hybrid method for generalized mixed equilibrium problems, zero problems, and fixed point of asymptotically demi-contracted markings in the intermediate sense. I actually arranged my presentation to be based on the following content, starting with the introduction. In the first part of the introduction, we are going to look at the definitions of some basic terms, which are quite relevant to our work. As we have just seen from the title, one of the key concepts related to this work is called fixed point theory, which is concerned with the problem of finding or approximating a point in the domain of T satisfying equation 1, known as a fixed point problem. And the collection of all such points is called the set of fixed points, usually denoted by f of t. So what is important here to understand is that whenever we talk about fixed points, one cannot actually escape from the concept of nonlinear operator, that is nonlinear mapping, for which the fixed point is to be approximated, which are of different classifications, such as non-expansive, strictly pseudo-contractive, and so on. But for the sake of this presentation, we actually limited our considerations on just few of such classifications because of the time constraint, starting with demi-contractive mapping here, which is defined to be a nonlinear operator satisfying inequality 2 with a constant k in the interval 0, 1 and non-empty set of fixed points. This is somehow generalization of many nonlinear mappings, as we can see from here, with k that is constant equals to 0. This part will actually diminish, so we'll be left with just this, what you have on the left-hand side, and only this, which corresponds to the definition of a very important class of nonlinear mapping called quasi non-expansive mapping with non-empty set of fixed points. And if you can recall also, there is what you call strictly pseudo-contractive mapping. So every strictly pseudo-contractive mapping with non-empty set of fixed points is also part of this nonlinear operator theory. And this is not the most general classification of nonlinear mappings. We actually have so many classifications more general than this one, as we can see here. For example, we have asymptotically demi-contractive mapping, which is also defined to be a nonlinear mapping satisfying inequality 3. We can see that the class of demi-contractive mapping is a subclass of asymptotically demi-contractive mapping with a null sequence kn equals to 0 and tn equals to t for all n. And we can see here with k equals to 0, this part will also disappear, and the remaining part corresponds to the definition of asymptotically non-expansive mapping with non-empty set of fixed points. So this is also a more general nonlinear operator. Actually, in 2013, Olaleru and Okeke introduced another class of nonlinear mapping, which is more general than asymptotically demi-contractive mapping. They call it asymptotically demi-contractive in the intermediate sense, which is defined by inequality 4 with a constant k in the interval 0, 1 and two null sequences Vn and Kn and non-empty set of fixed points. So this nonlinear mapping actually seems to be more general because it contains many important classes of nonlinear mappings as special cases. We can see with Vn equals to 0 here, this inequality will actually reduce to what we have in inequality 3, meaning that asymptotically demi-contractive is a special case of asymptotically demi-contractive mapping in the intermediate sense. So another property is called equally continuous. So when do we say that a nonlinear mapping is equally continuous? We actually say that it is continuous when for every two sequences in its domain, with their terms converging to each other or moving close to each other as n approaches to infinity, implies that their corresponding images also approaches or moving very close to each other as n approaches to infinity. What I have said can be seen physically or easily by considering this example. When we consider a nonlinear mapping T defined on a closed and bounded interval -8 to 10, defined as this, we can see from this graph that this is actually, there is a point of discontinuity for this map. The map is not continuous at 5, meaning that it is not Lipschitz continuous. We can also see for any two sequences we choose from this domain, as n tends to infinity, if their corresponding terms are moving very close to each other, maybe something like this, then their respective images also be moving to each other. So we can say that this nonlinear map is actually equally continuous and asymptotically k demi-contractive mapping with k in this interval and two null sequences defined as this. So another important problem which our proposed method is going to consider is called zero problem. More specifically, zero problem of inverse strongly monotone mapping. So what is monotone mapping? When do we say that a map is monotone? Actually, a nonlinear map is said to be monotone when the inequality is 6-fold for any two or for every 2 points in its domain. Let us look at this diagram. This will actually give us the clear picture of what I have just said in the above. You can see the nature of this graph is like this. For any 2 points we choose, maybe we choose x2 and x1 from here. Definitely we know that x1 is greater than or equals to x2. And their respective images also behave that way. The image of x1, the image of the function at x1 is greater than or equals to the image of the function at x2. So when we compute the difference between these images, there is the possibility, what we will get is positive. That is non-negative number. And here also the differences will also give us non-negative number. So the inner product will actually satisfy this inequality. But for this one, which is actually not monotone, one can easily see that we can produce so many points on the graph, which may actually fail that condition. For example, if we look at 2, we consider 2 and 0 as our x and y. For example, maybe x is 2 and y is 0. We can see that the value of x is minus 16, and the value of the value of the function at 0 is 0. So we have 2 minus 0 will give us 2, and minus 16 minus 0 will give us negative. So the product of negative and positive number will not satisfy this inequality. So that is why we can say that this is the graph of non-monotone mapping. So on the other hand, we also have what we call inverse monotone mapping. So what is inverse monotone mapping? Inverse monotone mapping is also a nonlinear mapping satisfying inequality 7 with a constant positive real number tau here. So the concept of zero problem, when we want to define the concept of zero problem, the zero of any nonlinear map refers to a collection of points in its domain at which the value of the function is, our mapping is 0. So we usually denote it by this particular symbol. T inverse of 0 is equals to this, at which the value of the function is equals to 0. We call it null space of inverse truncally monotone. Let us consider this example also. This is very nice example because it provides us with a connection between what we call a creative operator and strictly pseudo-contractive mapping. Sorry, we can see if we define a map A from H to H in this way, provided that T is non-expansive, then this is actually monotone. And 0 of this function, 0 of this mapping, sorry, will be is equivalent to the fixed point of T. So this actually provides us with the connection between zero problem and fixed point as well. In 2003, Funk and Hogg introduced or proposed another special type of monotone mapping. They call it relaxed eta alpha monotone mapping, which is defined as a monotone mapping satisfying in the condition given in 9 with respect to by mapping eta and function alpha from x to r, satisfying this. So basically, if we look at this, we can see that this includes many types of monotone mappings as special cases. For example, if we assume this eta of x, y to be equals to x minus y, then this problem will actually reduce to what we call relaxed alpha monotone mapping. Similarly, if we assume it to be x minus y, and the value of and we have two constants, maybe k greater than 0 and p greater than 1, then and alpha of x minus y equals to k norm of x minus y power p, then this will actually reduce to what we call p monotone mapping. And in particular, for p equals to 2, it reduced to what we call p strongly monotone mapping. So we can see that this is a generalization of many classes of mappings. And many authors have actually considered this problem in generating or in developing their iterative algorithms or methods of finding solution to many problems. As we can see here, Cheng and his associates actually studied that particular problem of relaxed alpha eta monotone mapping in the study of the generalized mixed equilibrium problem study given by this. They actually studied this generalized mixed equilibrium problem. They call it mixed equilibrium problem with relaxed eta alpha monotone mapping because of this part. This is mixed equilibrium because it combines at least 3 problems at the same time, where G is a bifunction defined by 13, and pi is proper, lower, and semi-continuous function, which is normally used to define what we call minimization problem. So this generalized equilibrium problem is also more general, when we look at it very well, you can see that if T is monotone, that is, if T is monotone, meaning that eta of y comma x is equals to y minus x, and alpha, that is the alpha we have in the definition there, is equals to 0, then this will actually reduce to the generalized mixed equilibrium problem studied by Peng and Yao. Similarly, we can see that if T of this, if this is pi is equivalent to 0 function, that is 0 function, then this will actually reduce to the equilibrium problem. We call it generalized equilibrium problem studied by Takahashi and Takahashi. Similarly, if the bifunction here is 0, this will reduce to what we call generalized mixed variational inequality problem. So actually, with this kind of generalized mixed equilibrium problem, one can easily study, you can study various types of problems in the with real applications. So this is what we are trying to study in this work. We are trying to propose an iterative methods that can actually study this to solve this particular problem. So in order to do that, the following assumptions are met. We assume that the bifunction, that is this bifunction G, actually satisfy these conditions from F1 to F4. So what the question of interest here is, we have presented at least 3 problems here. What is important to know is there are actually many methods of finding solution to such problems, but iterative methods remain the best alternative for finding solution to such problems. Consequently, many efforts have been devoted by different authors, by different researchers in this important area, and developed many iterative algorithms. For example, Nakajo and Takahashi, we know we have what we call man-iterative algorithms for approximating fixed point, Ishikawa's, Halpan, Picard iteration algorithm as classical iterative methods for fixed points. So in order to obtain strong convergence and relax so many conditions to obtain results, Nakajo and Takahashi introduced a strong convergence iterative method for man-iterative algorithm, and this is what they obtained. They call it CQ algorithm, where Cn and Qn here are half spaces, and they define their algorithm as a projection of the initial points to the intersection of these 2 half spaces. Similarly, Takahashi and his associates actually introduced another projection method. They call it shrinking projection method, which is not similar to the algorithm of Nakajo and Takahashi, because we can see in the Nakajo and Takahashi, they worked with 2 half spaces, while in this one, he dispensed the computation of maybe Qn, so he considered only one space, one half space. So he also obtained fast strong convergence for this particular problem. So as I said earlier, these problems, the problems of fixed points, 0 problems, equilibrium problems, actually have vast areas of applications. So because of their applications, fast convergence iterative methods are of much interest. So that is why many researchers in this area of research actually devoted their efforts in developing many fast convergence iterative algorithms, more especially in the sense of what you call inertial technique introduced by Polyak in 1964. As we can see that Menge also developed what we call inertial man-iterative algorithm. This is the iterative algorithm he obtained for non-expansive in Hilbert space. And in his work, he established the fact that this actually converges faster than the classical man algorithm without inertial parameter. Very recently, Abkar introduced new iterative algorithm for finding common solutions, because our work will be common solutions. So we are trying to look at the what you have in the literature for finding common solution of 2 or more problems at the same time. So he introduced a new algorithm for equilibrium problem and fixed point of finite families of dynamic contractive markers in Hilbert spaces. And this is a scheme he obtained. And very recently, can introduce the iterative algorithm for finding solution to system of generalized system of equilibrium problems and finite family of daily contractive mappings. This is the scheme. They obtain strong convergence because they actually use the projection method of CQ iterative methods. So our motivation, what motivated us to do this work, includes the following. The first motivation is we are trying to see how to extend and generalize this problem, this algorithm, that is the work for CAN in 12, from finite family of mappings, satisfying two, that is from finite family of demi-contractive mappings to a countable family of equally continuous mappings, equally continuous and asymptotically demi-contractive mappings in the intermediate sense. So at least here we extended the result from lower class of nonlinear operator to the higher class of nonlinear operator. And the second motivation is to develop an algorithm for solving system of generalized mixed equilibrium problems with relaxed eta alpha monotone mapping, not like what he considered here. In his own, he considered just a classical equilibrium problem introduced by Bloom and Oakley. So in our own case, we are going to solve the problem we presented in problem 14. And if we look at his scheme also, we can see that it is only used for finding solution to equilibrium problem and fixed point problem. While in our own, we are trying to develop an iterative algorithm that will consider another additional problem called zero problem, which is not considered in their work. And we are also going to try to find out if incorporating the inertial parameter in our algorithm will have any positive impact on the rate of convergence. So these are the motivations actually, and these are the preliminaries. The first lemma here is about the convexity and the closeness of the set of fixed points of equally continuous and asymptotically demi-contractive mappings in the intermediate sense. We applied it in establishing the fact that our scheme is well defined. We also use lemma 2, which provide us with the unique solutions to the positive integer equation 20, which are in and mn. We also apply this lemma for establishing our result because we are dealing with bifunctions, and we are dealing with bifunctions because of the equilibrium problem. So main result. In what follows, wherever we see in and mn, we are referring to the unique solutions of the positive integer equation we described in lemma 2. And trng here is a proximal operator described by 22, by equation 22. And this is the strong convergence iterative algorithm theorem we have. You can see we consider actually finite family of eta alpha, eta hemi-continuous and relaxed eta alpha monotone mappings. We also consider countable family of equally continuous asymptotically demi-contractive mappings in the intermediate sense with these null sequences. And this is with these assumptions, these are the assumptions we made. We assume that the conditions I to 4 to 5 of lemma 3 are satisfied, and the following condition is also satisfied, that is condition 6. Then the sequence generated by this algorithm, which is our proposed iterative method, converges converges strongly to the element in K, that is common element of the set of fixed point of Ti and 0 of AIs, and generalized mixed equilibrium problem. This conclusion, our theorem actually generalized and improved the results of Kahn et al. In the following ways. In the first way, system of equilibrium problems and finite problems of demi-contractive mappings are considered in their work, while in our own case, we consider a system of generalized mixed equilibrium problem with relaxed eta alpha monotone mappings and equally continuous mappings equally continuous asymptotically demi-constructive mappings in the intermediate sets. And apart from solving the fixed point and equilibrium problem, in our own case, we actually try to include another iterative, another nonlinear problem called zero problem. And unlike the algorithm, in their own, there is no inertial parameter. While in our own case, we introduce the inertial parameter in order to increase the performance of the iterative algorithm. Thank you for listening.
Any question or suggestion? Okay, if no any question, thank you for nice presentation.
Okay, thank you very much.
Okay, we on
Thank you,
Wins-
everyone. Ulailat is a very good and very nice talk all student, but sometimes I cannot attend, but I will attend some people in video because it's sometimes we meeting at the same time on afternoon of Monday, a lot of meeting, but I open follow you, but I did not focus and ask you, but I will discuss you later after I see all video record of you.
Okay.
Okay.
Yes.
Okay.
thank
Okay,
you.
Prof.
Thank you very much.
Thank you.
Okay, Professor.
Hadan.
Thank you. Thank you very much.
Mr. Solomon, I forgot on Wednesday we don't have us individual presentation.